First of all, let me thank you once again, Davide. Davide needs probably a little introduction. He's a professor at University of Zurich and leads a very dynamic group working on drones and perception and robotics as a whole. And as a personal note, Davide has been inspiring me under different directions, how to do even research from the reproducibility, dissemination. So it's with an immense pleasure that we have Davide here in a more intimate, if you want, occasion. And so, Davide, the stage is yours. Thanks again for giving us this opportunity to listen to your work.
So yeah, good morning, everyone. It's a pleasure to meet you today virtually. So I changed slightly the title of the talk, but the content hasn't changed. I wanted to be a little bit provocative. And now the title is Outperforming Human Pilots in Autonomy. So I've been working on autonomous navigation of drones using onboard cameras only and onboard computation now for 13 years. So I started in 2009. And I also brought a sample here that you can see on camera. This is an autonomous drone that only uses onboard cameras and an onboard computer, a Jetson computer. So it's a graphic processing computer. And this drone is very fast and is very agile. And I want to talk about this. But first, let me start from the historical details. So when did I start working on drones? I started working on drones 13 years ago. And this is one of the first videos that we recorded in my lab. This drone is completely autonomous. What you see in this video, the drone is just stabilizing. So it's remaining in hovering. And to do that, it needs a camera. So that's the key important thing about drones. Without images, drones cannot fly. Why? Because if you don't have GPS, you don't have any position reference. You cannot use an inertial sensor, so an IMU, because using an IMU, the drone would drift away and will basically crash eventually, because IMUs drift very quickly. So in absence of GPS, the only way to know the position of the drone, actually the full state, which is position, velocity, and attitude, is to use a camera plus inertial information. And that's very important because if you think of ground robots like humanoid robots, quadruped robots, cars, they maintain the feet on the ground. If they don't receive an image, they can still maintain the feet on the ground. They don't fall. But for a drone to remain hovering and not crashing, it needs to see. So that's the key difference from any other robot. That's why vision is so important. A drone without vision is not autonomous. So the drone here, it's basically using a software that extracts interest points that we call features, that are the one marked in green in the video. And then there is an algorithm called SLAM, simultaneous localization and mapping, that basically builds a map of the environment, also computes the 3D position and orientation of the drone with respect to the map. And so when you disturb the drone goes back to it because basically the position controller takes care of it. Using this map-based navigation, we demonstrated 13 years ago that you could navigate from A to B. And so the very, very, very first video of a vision-based autonomous flight is actually this one. You can notice that it's very old from the very low quality. I was actually the cameraman here, and this is a group of PhD students that I was advising. This was work that I did at the end of my PhD. So I graduated with Roland Sigbart at ETH Zurich. And at the last stage of my PhD, I moved to drones, and I used the SLAM, visual SLAM, to navigate drones autonomously. We gave a demonstration of this in the gym of the university, and the drone was moving from A to B using only features. The safety regulations of the university imposed that we would use a fishing rod to secure the drone, just to prevent it to, crazily fly away in case of issues. But the drone was completely autonomous and non-constrained by the cable that you see. This is a very dramatic moment of the scene. So this was also part of a competition, the European Micro Aerial Vehicle competition. And the competition was also about to enter through a window and then basically land. So we managed to pass through the window. but the drone was not aware of the window, so it was basically waypoint-based navigation. So it was building a map of the environment, and then in this map there were pre-computed waypoints, and then the controller was taking care of following these waypoints. On the top right, you see the onboard camera view. At the bottom right, you see the 3D map built by the drone in real time. The person that you see here, that is partially blurry, is a very important person. His name is Stefan Weiss. He also did his PhD with Roland Sigvart. He was younger than me, so I was advising him. So after he graduated, he took all this work and he brought it to NASA, Jet Propulsion Laboratory. He worked there for 5 years and he brought this technology to Mars. So Mars, as you know, features an helicopter since 2021 that has been flying autonomously more than 30 times and uses an onboard camera, an onboard computing, and an inertial sensor. So it uses the same technology that we demonstrated for the first time 13 years ago. Where else can we find today vision-based navigation? Well, there are a few companies that are bringing now vision-based navigation to drones. Companies like Skydio. Skydio is a company based in California, in the Silicon Valley, and they use as much as 6 cameras that you see here to build the 3D maps of the environment and then navigate the drone autonomously. And the main application are 3D scanning and inspection. So inspection of bridges, power lines, inspection of solar panels, all done autonomously, also in absence of GPS. So this is to say that thanks to the developments of computer vision perception, nowadays we can more or less deploy computer vision to make robots, mobile robots, truly autonomous. Which begs the question, what's next? Where are we? Where do we stand as roboticists in terms of, where we want to get? Where do we want to get? So, as you see, I think also in your lab, our aspiration as researchers is to make robots either similar to us in terms of skills and capabilities, but also maybe better than us, because by making robots better than humans, then robots can be productive and therefore can help humans in very difficult tasks. I'm thinking of inspection, I'm thinking of delivery, I'm thinking of manufacturing, think of Boston Dynamics. I mean, all their research aims at making robots that can work alongside humans or even replacing humans in very tedious, difficult, repeatable tasks. For me, I've been concentrating on drones. So my ambition is to understand how we can make drones, autonomous drones, fly as good or even better than human pilots. So as you can see, the trend is the same. We are trying to make robots as good or better than human pilots, because if we can do that, we can then make them very, very useful and very productive. What you see in this video is not an autonomous drone, but rather is a drone navigated by a human pilot. How does a human pilot navigate drones? Well, vision-based. They have a camera on board the drone. The camera relays the images to a headset. The human brain processes these images. It has a latency of 220 milliseconds. We measured it. And then it outputs a control commands through a remote controller. So human pilots are slow because, 220 milliseconds, it's actually quite a long time. It's a fifth of a second. Our algorithms are 20 milliseconds long, so 10 times faster than the human brain. But we cannot navigate so agilely and robustly as a human. So if you compare, what the human pilots are capable of doing today to what autonomous drones are capable of doing today, not just in research, but also, in companies, we are still behind the human pilot performance in terms of speed, versatility, which means the capability to adapt to new tasks and new environments, and especially robustness. So we want robots that can be deployed in the wild, in a non-structured environment, no matter the weather conditions, visibility, and so on. Why? Why do we want to do this? To increase productivity. That's the reason why we want to make robots as good or better than humans to increase the productivity. Think of Boston Dynamics, think of what you guys are doing, think of what I'm telling you now. This plot is a very important plot because on the vertical axis, you have the maximum distance that the drone can reach before the battery dies. And on the x-axis, you have the flight speed in meters per second. So when a drone hovers, basically, it doesn't cover any distance. So at 0 meters per second, you cover 0 kilometers. But as the drone increases its speed, linear speed, you can see that the distance that it covers before the battery dies is larger and larger. For example, at 6 meters per second, you can be guaranteed to reach 3.5 kilometers. By the way, this plot was computed for an average drone. Actually, we use a DJI drone here. What you observe, though, is that after 6 meters per second, the maximum distance covered actually decreases. Why? Because there is more air drag, and also you start consuming more battery energy. But there exists an optimal speed at which is very convenient to actually fly in order to maximize the utility and so the productivity of this drone. So imagine if you can have a drone that can cover longer distances, you can explore a building after an earthquake to search for the survivors. You can, for example, deliver goods in several locations, without having to replace the battery. And you can also complete the inspection of a bridge without having to replace the battery. So it matters to fly fast. By flying faster, a drone can fly farther. That's the idea. Where do current autonomous commercial drones stand in this curve? Where they're very disappointing. So these are the 3 best drone companies. We have Flyability from Lausanne, DJI from China, Skydio from California. Basically, these are the speeds at which they navigate. And this is the maximum distance that they can reach before the battery dies. So they are incapable to navigate faster, okay? And why? Because navigating faster actually implies a lot of problems. It raises a lot of challenges, as we will see. So now let's go to the core of this talk. This is the drone I will be talking about throughout this presentation. His name is Barracuda, or her name is Barracuda. Drone in German is actually a female word. In Italian is a male word. So this drone is also here, and it's vision-based. It has 1 or 2 stereo cameras. The number of cameras depends on what the drone is expected to do. And this drone has also a GPU. It's a Jetson TX2 processor, which is the brain. This drone is also very agile. As you can see at the bottom right, it can accelerate from 0 to 100 kilometers per hour in less than a second. It's faster than a Formula One. The weight is 0.8 kilogram, and it can experience accelerations of 5G, which is insane. It's as much as astronauts experience when they are launched with a shuttle. And these accelerations are pretty bad. So the solicitations that the drone experiences are so strong that there are a lot of unmodeled effects. So how do we control drones? You can use the traditional robot control architecture. There are 3 software modules: perception, planning, and control. Perception takes as input images, in our case, and the inertial sensors. It builds a 3D map of the environment and localizes the robot in the map. Then planning takes as input the map of the environment and computes collision-free trajectories, or one collision-free trajectory that then you execute that is then executed by the controller. This architecture has worked fine for 40 years. So all the commercial robots use this architecture. But there is a problem. It is insufficient for agile navigation. Why? Because it is slow, it is fragile with imperfect perception, and ignores nonlinear aerodynamic effects. Because you need to model everything. That's a problem. What are typical problems when you fly fast, agilely? So from now on, I will not just say fast. I prefer to call it agile navigation because agile is much more general than being fast. It means also how quickly you can change the rotation, okay? Your orientation. So that's the agility, is the capability of a robot to change its direction. So when you fly agilely, you experience motion blur that you see here. You also experience quick changes of illumination due to the fact that the camera suddenly is expected to change completely the direction of viewing. And so some parts of the image may appear overexposed or underexposed. That means that your drone is completely lost. You won't be able to find the goal. You won't be able to detect and track features that you need for the estimation. It's a mess. And more importantly, when you are flying fast, you generate a lot of aerodynamic effects, some of which are very difficult to model. And I'm thinking of rotor-to-rotor interactions and turbulences. Why? So you see, the rotors are very close by, and they generate, vortices. They interact with one another. Another problem that you encounter when you're flying very fast is that you are generating air, you're pushing down air, and you fly into your own air. So you generate these vortices. These vortices, as I will tell you later, can cause a deviation from the trajectory. It can be by several meters. And they are very difficult to model. The only way to model them is to basically use computational fluid dynamics simulators, but they can take ages to compute. So we are now exploring deep networks. Same applies for the other two things, fragility of perception, motion blur, and so on. We can deploy machine learning. So this is to say that machine learning can be very useful. If you ask a machine learning person, it will tell you that in principle, this is a provocative slide. And if you ask DeepMind, they will tell you, you can build a neural network to replace the current state-of-the-art of robotics. So you could build, in principle, one day a neural network that takes a sensor inputs and maps them completely to control commands. We humans, animals, are the living proof that this is possible. So this will be possible. But as you can imagine, at the current stage, you need tons of data. So it's very sample inefficient. You would have to record data in every possible condition that you want your robot to navigate. That also means any weather conditions, any possible environment. And even if you could do it, though, it would have very limited interpretability. How do you know why the network failed? So what we are doing, or what we have been doing in my lab, is something in between this approach and this approach. What is it? The idea is to combine each model-based method with a network that tries to model things that cannot be modeled by first principles. That's the idea. In some cases, we have even replaced entirely these modules with completely learned modules, or we have combined some of these submodules with deep network components. Now, I would have to go too much into detail. I refer you to the publications that I will present later. Now, when you use deep models in robotics, then this raises several questions. Should we train it with supervision or without supervision? And how do we get enough training data? Can we possibly learn in simulation? If you learn in simulation, how do we address the simulation to reality gap? And if you manage to make it work in the real world, can you make it generalized to different real world environments? These are the key questions that we're facing, me and also our entire community. So I will focus in the remaining of this talk on three tasks: acrobatic maneuvers, navigation in the wild, which means in unknown environments, and autonomous drone racing. Why autonomous drone racing? Because it's the only task where you can really quantify the gap between autonomy, algorithms, and humans. Because in drone racing, there is only one parameter that you can use to quantify how far you are from the human, which is the time to finish the circuit. So the fastest wins, like in Formula 1. So I will focus on these three things. I will start with the first two, which are acrobatic maneuvers and navigation in the wild. Let me show you a few videos, and then I will tell you how it works. So the first one is autonomous drone acrobatics. The drone you see here is, again, this one is this drone. It uses only a stereoscopic camera and the onboard computer to perform these acrobatic maneuvers. The drone over here reaches accelerations of 3 Gs, which are the same accelerations that human pilots experience. And this was the first time that an autonomous drone was using onboard sensors. Before, these things were only possible with GPS or using motion capture systems. And this one was controlled by a neural network, actually by neural controllers. I will tell you later. Let me show you another video. This one is the same drone that now is doing another task, which is navigating in the wild. It means in unknown environments. For example, in a forest, in a structured man-made environment, like a search and rescue, in a hangar. This one colliding was a commercial drone. Again, in a forest. You can see how shaky the robot is because it's moving super fast. It's navigating at speeds of up to 40 kilometers per hour completely autonomously. And even with some degraded visibility. Here, there was a little bit of fog. Now, also in this case, there is a neural network in charge of doing something. So these two videos I showed, basically, they are using some deep models inside. These models were not trained in the real world because it would be impossible. It would be too costly. It would endanger my PhD students. But rather, these deep models were actually trained entirely in simulation. On the left, you can see we used Gazebo. On the right, we used a real engine. Actually, we built a simulator based on a real engine, which we also released. It's called the Flightmare. So why do we use simulation? For several reasons. Simulation is fast. It allows you to train on an almost unlimited amount of data in reasonable time. Usually it takes one night to train these models or multiple days, depending on how much data you want to use. But so it's reasonable. It is also cheap because you are not using the real drone. If you would use a real drone, you would have to actually repair the drone every time you crash. And imagine you are crashing many times, even in simulation. Imagine if you use reinforcement learning, even worse, because you learn by trial and error. And another reason, it's very safe. Simulation is very safe. It does not endanger anyone, okay? And it's very cheap. So these neural networks were trained with an equivalent of 60 simulated days of 24/7 flight in just 5 hours. 60 simulated days in just 5 hours. So that's the amount of data that we used. But there is a problem when you train in simulation. The problem, you see it here. For example, for the case of navigation in the forest, the images of a forest in simulation are very different from the photorealism that you have in the real world. So they are not photorealistic. This is called the simulation to reality gap. Of course, nowadays there are very expensive photorealistic simulators. I mean, think of Hollywood. You can make a whole movie with the real actors all in simulation. But the problem is they are very, very slow. And there is also another point. So not only there is a gap, but also the real world can differ in any case from the simulation because you want to make sure that it generalizes to different types of forests, no matter the season. For example, a forest can appear green, yellow, or red, depending on whether it's summer or winter or autumn. It can also change the appearance depending on how much light is present. So in the dark, it will be different than during a bright day, and it will be different during a cloudy day. So how can you generalize such that when you train only in simulation, when it sees the real world for the first time, it flies without any fine-tuning? That's what we are aiming at. We are aiming at zero-shot sim-to-real transfer. That means you train only in simulation, you deploy to the real world without any fine-tuning. How can we make this possible? So there are 3 different techniques that are known. There is a domain randomization. You randomize all the features of your simulation environment that you want your environment to be invariant, your policy to be invariant to. You can also do some fine-tuning in the real world, but we didn't want to fine-tune in the real world. But there is another aspect that is often neglected. You can also not train on what you see, but you rather train on an intermediate representation. So this was the idea of these 2 papers. We didn't train the network on raw image pixels, but rather we trained the neural network on depth maps. Since we have a stereo camera, we can triangulate the points, and then the input to the network are these depth maps, where each pixel intensity encodes the distance from the camera. Yellow means close, black means far. Why did we do that? Because now depth maps are similar in simulation and in the real world. They are unaffected by the amount of illumination, the type of color, texture, and so on. It doesn't matter if your trees are green, yellow, red. It doesn't matter if the texture of the trunk of the trees is different. They are always the same depth maps. So they should be able to generalize to the real world. And it's actually correct. It did generalize to the real world. What you see here in this video is what the depth maps look like in simulation when we train in simulation. By the way, we don't train on ground truth depth maps, but we train on realistic, noisy depth maps that were generated from left and right stereo simulated images. And you can recognize that because if you look carefully at the trunks of the trees, there are these beautiful occlusion artifacts that appear yellow. This is due to the occlusion of the left and right images. So they are realistic depth maps. When you look at the depth maps of a drone navigating in the real world, they are indistinguishable from the ones in simulation. Now, how did we train this architecture? Well, we trained the architecture via privileged imitation learning, where the idea is that we distill the knowledge of an artificial expert into a neural network. Or saying that differently, we are trying to have a neural network imitate the output of an artificial expert. Who is the artificial expert? So first of all, who is the expert? The expert shouldn't be a human because we want to be better than a human. So for us, the expert is an artificial algorithm that is the best state-of-the-art algorithm. For example, we took the best trajectory planner. So the expert is an algorithm that can take all the time it needs in simulation. It doesn't matter how slow it is. It's only for training. The artificial expert basically is for us the best state-of-the-art global planner that takes as input all the knowledge of the forest. So it knows perfectly the position, orientation, and density of the trees. That's why it's privileged. So it knows basically the ground truth, and it generates the ideal trajectory. And then we have a student network, which is a convolutional neural network that also outputs a trajectory that should imitate the one output by the artificial expert. So the loss function in this case is the difference between the 2 trajectories, the one by the network and the one output by the artificial expert. Now, what's after the trajectory? In principle, you could also ask the neural network to generate control commands. In this case, you would have then an end-to-end mapping from sensory inputs to control commands, but we didn't want to do it. Why? Because we wanted our policy to generalize to different drones, different masses of the vehicles, different aerodynamics, different sizes, different inertia matrices. So what we are doing is that only we ask the network to output a trajectory, but then this trajectory is executed by an optimal controller, a model, nonlinear model predictive controller, NPC. This way we maintain we keep the generalizability, so we can generalize to different drones, and we maintain the interpretability because NPC has certain guarantees, and we know when something goes wrong, it's the fault of the NPC. Otherwise, it's the fault of the neural network. So Basically, that's how we did it. Now the question is, okay, so we are using this neural network to basically replace. So the neural network now is bypassing the perception planning part. It's basically completely replacing the perception and planning modules. It's now a single module. So it's expected to be faster because it's a single module, but we also especially expect it to be more robust. That was the original idea of doing it in the first place. We wanted to see whether this network can generalize to environments that are affected by noise in the data, motion blur, dynamic changes of quick changes of illumination, missing pixels, and so on. Well, let's see how good it is. It's actually very good, and it's also much faster than the state of the art. So let's talk about speed, computational efficiency. So in the paper, so the paper was published in Science Robotics last year, 1 year ago. Here you see we are comparing our algorithm against the best of the art, which is the fast planner from Xiaozhe Shen, Hong Kong University of Science and Technology, which is open source. Their algorithm takes 65 milliseconds per depth image. Ours takes 6 times less. So our algorithm is 6 times more efficient. Why? Because we are not building a map and then generating thousands of trajectories, computing collision checks in order to select the ideal trajectory to execute. We are bypassing this stage completely. The network learns to associate that map directly to free space directions. And therefore, that's why it's so much faster. Not only it's faster, it's also more robust. For example, here we have plotted the success rate versus the flight speed. So we expect that as you increase the speed of the vehicle, the success rate diminishes, which is the case. Because if you go faster, you have less time to make a decision before the next obstacle appears. But our success rate is much higher than the state of the art. It's actually much higher to a point we can fly twice as faster than the traditional baselines. So for example, we can fly up to 10 meters per second with a 60% success rate. So it only crashes 4 times out of 10. What does it take to reach 100% success rate? Well, ideally you would like to have a faster sensor like event cameras and maybe an even faster network. But this is actually future work. So what are the takeaways of this part of the presentation? There are two takeaways. So I showed that it is possible to distill complex navigation tasks into neural networks. I have also showed that by combining model-based approaches with the deep models, the entire pipeline is now more robust against sensor noise, and it's also faster because you don't have anymore this compound latency. I've also mentioned that if you don't train on raw image pixels, but on some intermediate representation, for example, dead maps, you can then transfer to the real world without any fine-tuning, so zero-shot learning. But we were training the network here using privileged imitation learning, so by imitating an artificial expert. Now, what if this artificial expert is not available? Then in this case, you cannot train with supervision. And then we need to use reinforcement learning. And that's the topic of the next chapter. So 5 years ago, we started working on autonomous drone racing. Now I'm going to share a video, and I hope you can hear the sound. Let me know if you hear the sound, please. Can you hear the sound?
No, Davide.
No? Okay, well...
probably there are three
just watch
dots.
The video, it doesn't matter. Watch the video.
If you want, there are okay, because there might be the possibility to
doesn't
share.
Matter. It doesn't
okay.
matter, actually.
Okay.
Just watch the video. I mean, this is the Swiss champion of drone racing. His name is Marvin. He's 15 years old, and he's flying at over 80 kilometers per hour, and he's a world-class pilot. So he has won a lot of competitions in Switzerland, in Europe, around the world. He's one of the best, but not the best. But he's impressive, and he's very, very young. Actually, what is interesting is that the best human pilots happen to be the youngest ones as well. Now, drone racing is a very, very difficult sport. And it's also so difficult that actually the drones are always constantly pushed at their physical limit. They experience accelerations up to 5G. Yesterday, I did a parabolic flight in Switzerland. I experienced 2.5 Gs. I felt very, very sick and experienced for the first time what these drones experience, but actually experience much more than that. So this is to tell you that it's very difficult to control drones at these high speeds. Let me show you some spectacular crashes of Marvin, so our human champion. These are all crashes, all complete crashes. So Marvin destroyed a lot of drones, more than 100 drones. Most of the times we can repair them. So it's okay, but of course it consumes a lot of time. Now we want to fly like Marvin, or maybe better than Marvin. So we need to talk about autonomous drone racing. What is autonomous drone racing? In autonomous drone racing is defined as the problem of generating control inputs for the drone that minimize the flight time through a series of gates. So you want to pass through gates in a given order, and the first one that reaches the finish line or the finish gate wins the competition. So it's like in Formula One, except that now you have doors to pass through. This sport, drone racing, has become now very popular. And typically, the difference in times between the first and the second human pilot is a tenth of a second. So 100 milliseconds. That's very little if you think about. Any little mistake can cause a loss or a crash, and you want to avoid it. So basically, in autonomous drone racing, you want to find a sequence of control action, so control commands, that minimize the total time to finish the race. Okay, subject to system dynamics, input constraints, state constraints, physical constraints. So we started working on this problem 5 years ago. And at that time, we were not even thinking about deep networks or machine learning. So we started working on optimal control. And so I hired some control people, and we decided to split the problem into two parts. First, to compute a time-optimal trajectory, so the ideal trajectory that minimizes the time, and then execute this trajectory. So we came up with a paper that was also published in Science Robotics last year, that you see here at the bottom, time-optimal planning for quadrotors waypoint flight. It was the first algorithm to generate a minimum time trajectory through a series of gates in minimum time that exploits the full quadrotor model. I'm saying this because previous models used polynomial trajectories, which are suboptimal by definition. Bang Bang, for example, is not a polynomial trajectory, so you need to be able to incorporate that. So we are using numerical optimization here, and look at this animation. This is how the algorithm converges. So you can start from a random trajectory, and then poof, after 3 hours, yes, it takes 3 hours, it finds the optimal solution, the time-optimal solution. And you can see what it looks like in 3D. Here you can see that there were two gates on top of each other. Two gates on top of each other are super difficult, even for human pilots, because there you can waste a lot of time. Now, the problem is actually to execute this trajectory. So look at this image. So the blue one here is the time-optimal trajectory. And what happens though often is that you're using now a camera, not GPS, no motion capture. You're using an onboard camera to estimate the state of the drone, so position, velocity, and attitude. At these speeds, you will experience a lot of drift instead estimation. Aerodynamics, the images will also be motion blurred. So effectively, you are not executing the blue trajectory, but you will be executing a different trajectory, which is no longer optimal. It's suboptimal. But that means you won't beat the human. We found also another problem. Even if you could execute this trajectory, you need to tune classic controllers to possibly execute this trajectory. So we have been using MPC. Then we moved to MPCC, which is nonlinear model predicted contouring control, where you also try to maximize the progress along a trajectory. It would take us weeks to tune these controllers. even months, but we were still under the performance of humans. So we had to move away from classic controllers. So at the moment, we are no longer using MPC, neither MPCC, neither L1 adaptive controllers. We are using RL completely, model-free RL, reinforcement learning. I'll talk about that in a moment. Let's talk about perception. How do we localize the drone? We localize the drone with a camera, a single camera, exactly like the humans. We have a neural network that is dedicated to detect gates. So it's been trained in simulation plus real-world data to detect gates. It can do it pretty well, most of the times. But it's very uncertain. Here you can see in pink the tube of uncertainty that the drone state estimator experiences. As you can see, when you approach a gate, your uncertainty actually increases because suddenly you lose the detection of the gate, and then it shrinks when you pass the gate because you perceive the next gate. But this tube is quite large. So you have an uncertain state estimator, and then I told you it's very difficult to train controllers. So we are using a neural network to replace basically the complete model. So the neural network takes as input position, velocity, orientation that come from the camera, from the gate observation, and then it outputs control commands. This neural network is a simple two-layer, multi-layer perceptron, a two-layer MLP, very simple. And this network is trained via reinforcement learning. We use PPO. Now, you know, the reinforcement learning, you need a lot of data. So to make this faster, more efficient, at training time, we deploy 100 quadrotors with different initialization points. The whole training takes only 3 hours, which is equivalent to 60 full days of flight time without sleeping, 60 full simulated days. Now, what is very important in RL is the designing of the reward function. In our case, the reward function consists of 3 terms. A progress term that maximizes the progress towards the next visible gate. So you try to minimize the time towards the next gate. It also has a perception term, because remember, we are using a camera to detect the gates. So you want to maintain the visibility of the gates. And then it penalizes every time you miss a gate or you crash against the gate or against the walls. Let's see how it works. Here you can see our vision-based autonomous quadrotor flying in the real world. It flies at speeds of 80 kilometers per hour and is the fastest vision-based drone ever shown so far. Completely autonomous. It's this drone, the one I'm holding in my hands. You know, having a RL controller is not enough. Modeling the uncertainty is not enough. The key problem are aerodynamic effects that can be very, very prominent, especially at these speeds. Can be so prominent that the difference between the desired trajectory and the executed trajectory is as much as a meter or more. So we are also collecting data in the real world to improve our simulator. So here we need to do fine-tuning in the real world. So how do we do the whole thing? So this is the key idea. We train first the policy in simulation. We deploy it in the real world. We collect a few data. We go back to simulation. We use the collected data in the real world to improve the simulator. We fine-tune in simulation. We deploy finally to the real world. So basically, that's how we do it. The first policy is trained in simulation, but will not be human pilot performance. We deploy in the real world to be able to capture the real world dynamics, and we use motion capture at the moment for doing that. Then we come back to the simulator. We use these trained residual models to improve the simulator. Finally, we deploy completely vision-based, completely autonomous, no motion capture in the real world. Does it work? So after 5 years of work, we decided to invite to Zurich the best of the best. And that happened a few months ago, June. So we invited the best world champions of drone racing, Alex Vanover from the US, Thomas Bitmatta from Australia, and of course we invited our local champion, Marvin. This was also featured in SuperQuark Rai Uno a few weeks ago in July. This is basically the recording of the event. The blue drone is the AI drone. The red drone is the human piloted drone. You can see that the blue is ahead of the human. So yes, we won. By how much did we win? We won by half a second. So these are competitions where the difference between the first and the second winner are usually a tenth of a second. We were 5/10 of a second faster. That means the AI can beat a human using only onboard vision. Does it mean, though, that we are able to compete against humans in any conditions? No. In fact, in terms of number of wins, we are below humans. So we perform many races, but the AI drone could only win 40% of the races, while the humans could win 60% of the races. This is because perception is very, 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 very difficult. So there are a lot of problems whenever the images are distracted by motion blur, unmodeled visual effects, like at some point we had to open the doors of the hangar to let some light. That light distracted the vision-based algorithm. So perception is one of the most difficult research problems of today robotics. And perception is not solved. That's why we don't have autonomous cars out there. And this will take decades to solve. So yes, humans still have a chance against algorithms. That's the good news. So in conclusion, I showed that learning-based approaches can allow to fly superhuman under certain conditions, so in control conditions still. I also showed that learning-based, so deep models can be more robust than standard models. They are also faster. I also showed that it's possible to train sensory motor policies in simulation and deploy them in the real world without fine-tuning, zero shot, or with a minimum of fine-tuning by collecting some additional data in the real world. I talked about also aerodynamic effects, but there are many, 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 many things that are still unsolved. For example, what does it take now to fly in any environment? So a generalist AI, so that you go in any possible environment to navigate. Can you generalize to new tasks and also to new platforms? So there is a lot of questions still that are to be answered, and we are focusing on. And with this, I would like to thank you for your attention. And this is the team behind these slides. Thanks a lot.
Thank you very much, Davide, for the great talk. It's always really somehow fascinating to see your progress, and also the yesterday flight, 0G flight. And then I wanted to ask you something more because I was interested. So, but let's open the time for question time. So, anyone who would like to ask questions, do not hesitate to open your camera and start the question. This is a shy audience, so I will start. So I break the ice, David. So I have a question on slide 17, because if I remember correctly, so you said that when training between the simulation and the real environment, you had this fog, and you depth the depth map. So my understanding is that you are basically creating an abstraction layer.
That's right.
Of the environment. So right. Then the first question that I had is, okay, so how probably then the general question is, how do we find abstraction layers which fit our case? I don't know if this makes sense or
it makes a lot of
not.
sense. Indeed, it's a very good question. We're working on that. So I showed two works, but I only showed you the intermediate representation for the navigation in the forest. So for the forest, we used a depth map. But for the case of acrobatics, we didn't use a depth map. It wasn't necessary. We used the feature tracks, so optical flow vectors, because optical flow vectors are similar in simulated gazebo environments and in the real world. How did we find this intermediate representation that you call representation layer? By chance, by intuition, human intuition. That's the point. in general, you want to find a representation that reduces the gap between the observation models in simulation and the observation models in the real world. So at the moment, we just basically did some search. We tested a few ones and we checked which ones would reduce the so-called Wasserstein distance between the observation models in simulation and the real world. In practice, what you would like to do is representation learning. So you would like to learn a representation that allows you to solve the task. So you could use, for example, an autoencoder that, for example, allows you to go from the input image to a latent space, and you want basically to learn what that latent space stands for. You
Okay,
can train that end to end.
Okay.
You can train that end to end.
No.
We are working on it. We just uploaded the paper to archive, or we are going to upload it. So we submit the paper to archive, which is about that, learning representations for autonomous drone racing. And you can see there how it works. However, it worked from simulation to simulation, is still not working from simulation to reality. So that's the next stage. So that's the point. You know, transferring to the real world is still very, very difficult. And so it takes a lot of work. We don't have general solution. It depends also on the task. It can be solved for tasks like grasping, but now navigation in real world environment is more complex. So probably what we will have to do to generalize to the real world there is to use a latent space that has a higher dimension rather than too small dimension. Also, you can play with that.
Okay, no, okay, yeah, that's great. Then I had also another question. So concerning the learning part, because this is really interesting. Okay, so we are clearly in the business of trying to control these humanoids, and we also implemented the three-layer architecture, so which each of these blocks have its own logic, but I mean, one of the probably of the additional complexity that I see between, for instance, humanoid robots and your case are basically two. The first one is that the complexity of the mechanism, which because we have higher degrees of freedom, so we have a floating base plus the internal degrees of freedom. And then there is really what somehow is a pain in the neck, which is contacts. Okay, so
yes,
contacts with the environment is screwing up everything. Okay, so it's really difficult to model them, then it's really difficult to learning and etc. At the fundamental level, the first point creates somehow some redundancy given a task, and the second creates uncertainties given the task. So I wanted to ask you your opinion on this. So have you ever dealt with a higher degrees of freedom drones like manipulators, flying manipulators, which make also contacts with environments? And what's your feeling about the generalization of the approach you showed us today, which could be applied as well in the case of, let's say, floating-based systems, high number degrees of freedom floating-based systems which make contacts with the environment?
The answer is no. I have not done any work where we actually have manipulators, neither on a ground robot or a legged robot or a flying robot. But Marco Hutter, who is a professor at ETH, has done this work. So they use similar approaches to ours. For example, privileged imitation learning, or now more and more reinforcement learning, where they actually train in simulation. Of course, the models learn in simulation differ a bit from the reality, and then they go to the real world. They use it. Basically, what they do is that they add a neural network on top of the first principle models that basically tries to model the effects that you cannot model in simulation. Then when you go in the real world, basically by using data from state estimation, for example, they use a camera or a LiDAR, then you use this as a supervision signal, and then they train these residual models. Then they go back to the simulation, and then they use these residual models to improve the simulator, and then they do the training entirely in simulation. So they published 2 papers in Science Robotics where they walk their quadruped robot in different wild environments, even on the Swiss Alps, even on grass, on off-terrain, using basically these residual models that was trained with reinforcement learning. So it can be done.
It can be done. Yeah, it can be done for sure. Yeah, we know the Marco's work, and it would be an interesting direction to go along humanoids they have their own specificities with respect to quadrupeds, but indeed it is a unique occasion to take a look at. So I stopped asking questions, otherwise I monopolize the thing. So let's reopen the question time from the audience in the case you have any. So anyone from the audience? Yes. Okay, so we have, yes, proceed.
Hello, hi. Thank you for your presentation. My question is related to the specifics of the success-fail rate of the navigation planner. You said when compared to the fast global planner, it succeeded 60% of the times. The rest 40%, was it because it could not find a path, or that it found a path and the path led to a crash?
So it all depends on the sensing range and the latency of the system. So the maximum speed at which you can fly in a forest depends on the sensing range, on the latency of your processing pipeline, which includes the latency of the perception, the latency of the controller. And then, of course, it depends on the density of trees. So in the paper, there is we compute the maximum theoretical speed that you could possibly reach. It's 13 meters per second. That assumes that the latency is always below a certain threshold. Here you are seeing the perception latency. Then there is the mechanical latency, which is the time that the robot needs to steer and then avoid the trunk. And so basically what causes the crashes 40% of the time is the fact that, depending on sometimes the complexity, for example, you can get the reasoning, the action a bit too late. And then, of course, then it's too late to possibly react against the obstacle. It's as simple as that. So you would like to reduce the latency, perception latency, even further, for example. That's as simple as that.
Okay, thank you.
Okay. Anyone else from the audience who would like to ask questions to Davide? Okay, so it seems that question time is about to expire. So in the case, anyways, other questions, you're welcome to ask. Davide, so at this point, I really want to thank you for your great talk. And let's hope that actually we can, in the future, we might work together along these interesting topics you just presented. I want to thank you very much. And in the case you pass by, you are more than welcome to visit the lab to take a look at what we're trying to do here. Okay.
Absolutely. I wanted to just say two things. So tomorrow I will be in Rome for the IRIM conference. I will be there only tomorrow from the morning until the late evening. So if some of you want to approach me, feel free. I will be very happy actually to interact with you guys. And I also have open PhD and postdoc positions, and also visitors. So I think we are talking now with a student of yours from Daniele about possibly having him visit next year. And also we also take interns, like people who want to do a master thesis, for example, in our lab. So there are different ways to come here. Okay. And yeah, thanks a lot for your attention and your question. And
thank you very much, Davide. I'm sure that this talk will inspire us for the also next directions that we can take. Thank you very much, Davide.
Thank you, guys.
And see you soon. Bye.
Bye. Bye. Bye. Thank you. Bye.
Bye.